All right, we have something a little different now, um, simply because I made some slides for a research presentation that I was going to do with people I work with, but I did not end up presenting the slides. So I figured rather than just have them sit in my computer till, the end of time, that I would simply make a quick video and share this information. It's very much a difference between um, what I usually do, but perhaps it's good forecasting for some ideas I have in the future. Um, but we will have to see. Um, we'll have to see. I have some ideas for reinforcement learning in the future, and paper discussions in the future, but we will see what comes of it. But for now, we're going to be talking about two papers, the first of which is the decision transformer, which is a offline reinforcement learning algorithm that basically disregards everything we think we know about reinforcement learning. So in this offline paradigm, right, you have just data sets, sort of similar to supervised learning, where you just, reinforcement learning, you usually think about the interaction with the environment, but now we're just saying, given interactions that may or may not be optimal, uh, do the best that you can at inference time. And so this decision transformer doesn't use, a lot of times you'll see value functions or you have your policy that you're computing advantages with and lots of fancy things, right? Decision transformer disregards all of that and simply models it as a sequence prediction problem, similar to a lot of NLP tasks. So what does this mean? This means that at any given time step, um, it's trained to predict the next action. It sees state action reward tuple, and then it says, okay, what's the next action? And that's all it predicts, and all it's ever going to predict. It never tries to predict reward. Um, it only tries to predict the action. So it's really simple in that thing. It's just simply saying, given this information, what's the next action? And then it's updated with a loss function with the true data set. In the case of like continuous control, you can just do a mean squared error of the true next action, and in this case in the offline variant. And the transformer architecture is simply a GPT style architecture. So it sees the last 30 states, actions, and rewards. So there's a total of 90 tokens fed into this transformer. But it's worth noting that the reward is not so trivial because in this offline setting, we're not predicting rewards. And in fact, we're not even optimizing for rewards. So if it sees, right, let's just take an example of a mediocre Pong player. It sees reward of +1 as a given state predicted next action. It's going to try and do the action that that person did, and then at inference time it's basically going to just be behavioral cloning in that case, which is not desirable, because if we have mediocre performance, we want to do better than that at inference time. And so the way we do this in the work, or the way they do this in the work, is by doing returns to go. So at the start, right, you have the maximum, and then as you go along, it goes down until you're at 0 rewards, right? So if you start at 300 points, right, the offline, you know how much it's going to have, right? You're basically just reversing the ordering. So if you're like, I have a breakout run that goes and achieves 300 points, at every step you go through, you're going to say, here's the state action reward, or the 30 state action rewards, and each reward is going to be decremented by the reward given at that time step. So if you take action and you get a +1 reward, then you're going to see your next R hat is going to be 299 rather than 1. And so you can just at inference time set it to the highest, or 1, or if you're normalizing it, right? So then you're saying, okay, if you're normalizing it to whatever the maximum score is, then you can just say, okay, I want the maximum score, and it will try and give you that maximum score based off of this information. And of course, there's the embedding, and it has positional encodings, and then there's a linear decoder. So it's just a dense neural network layer. So the results, there's pretty good results. And then, yeah, that's just the standard graph and the standard bolded, results that you'll see in every RL paper. And now the question, one interesting question is, how well does it actually follow your commands, right? If you say, I want, right, you're telling it, I want 10 rewards in Pong. And then it's like, okay, I'm going to go, because that's what the trajectory is, right, in our offline sampling. Well, then how well does it actually follow that? This is what it shows here, is that the oracle is what you're telling it to get. And then your decision transformer is what it actually gets. And then your best trajectory and data set is just where the optimal and the best performing one is in the data set. So for example, if we look at Pong, you'll notice this is a 1-to-1 ratio in each case. The oracle, right, at 300 desired performance would get 300 actual performance. We can see in Pong, in this case, this is a good example, right, where up to this point, it does almost exactly what you tell it to. If you say, get 110 points, it'll get you 110 points almost exactly. However, after that, if you're like, okay, give me 150, it's going to fail, and that's likely because it hasn't seen anything better than that. However, sometimes, like in Pong and Qbert, for example, it really doesn't do any better than the best example. Sometimes it is able to do substantially better than the best example, like in Sequest. So this is an interesting sort of concept. There's been a couple of papers that have extended it, offline reinforcement learning as one big sequence modeling problem. I think this one came out like simultaneously, so there's not too much different from it. There's generalized decision transformers, and so that one is sort of just expands on the model and makes a general form of it that you can plug and play with, right? So you can have learned reward functions or bend reward functions, all sorts of stuff. And then the last one is an interesting one. Can Wikipedia help offline reinforcement learning rather than just using the GPT architecture? They literally plug in a GPT model or a similar pre-trained language model, and it shows promising pre-trained capabilities, which is kind of surprising, at least to me, because sure, like you expect sequence prediction to perform well for these sort of GPT models, but to do well at offline reinforcement learning seems like such an out of distribution task that I'm impressed that it's able to do well at all. Now our second paper, and I should say that both of these will be below. Our second paper is Curiosity-Bottleneck Exploration by Distilling Task-Specific Novelty. And so this paper, I believe, was at ICML 2019, and presents, I should go to the next slide, presents a method for intrinsic curiosity rewards. So this was a common, still is, I guess, but it was especially like 2 or 3 years ago, this intrinsic curiosity. There was a couple of papers like R&D and stuff that were really popular. But a common problem is the intrinsic reward can be task irrelevant. So if you're desired, if you're saying, oh, look, this is a new state, but this state is completely unimportant to my task, then that's not necessarily what we want, right? We don't just want the agent to visit new states for the sake of visiting new states. We want it to visit new states with the end goal of exploring paths that will lead to a higher reward. So the way they do this is they rely on an information bottleneck. So for some input X, distribution X, and target distribution Y, and the latent representation Z, which you'll see is very similar to some sort of variational autoencoder, the information bottleneck objective is to minimize the mutual information between the negative mutual information between Z and Y, and the mutual information between X and Z. And so mutual information is basically just a measure of how similar, in some sense, or what the dependence is between these two variables, or the amount of information that you can get from one variable by looking at the other, right? So if you had perfect information, right, you would be able to perfectly predict y from z. And so that's just an example. And you can do some math and you'll be able to derive their curiosity novel metric, which is the KL divergence, which is a asymmetric measurement of probability distribution divergences, from the probability distribution of z given x, where x is a specific example from the input data set or probability distribution, and q of z, where q of z is the variational prior, or the variational distribution, not prior. And in sort of the ideal case, this would be 0, because p of z given x is approximately equal to q of z. So right, when this has reached 0, then the probability distributions are the same, and so our intrinsic reward is going to be 0. And so that makes sense, right? When the more training we have, the closer these distributions are, and so the more we probably visited that state. And so here's the actual method. At rollout, we have our environment that gives us our extrinsic reward, our state x of t, and our policy pi. From this x of t, we compute our intrinsic reward by feeding it into a compressor, which is just a neural network that has a smaller latent space. We compute the intrinsic reward using this KL divergence, and you can see the bottom, the closed form solution for this. And then we, from this latent space, predict the value, and we can optimize it, since it has constant variance, to just be the mean squared error with the value. And then we can minimize this function using just the sum of these two terms. And so we can see that when our error is 0, this is going to be minimized, and when our internal reward is 0, this will be minimized. So what we're saying is that, right, when these two probability distributions are equal, the KL divergence is going to be 0, and these two are going to be equal after many visits, basically. So if we look at an example, we see x of t is a observation that is a relevant observation. Basically, x of d is irrelevant. So we can see that in this case, the gradient of the two terms that we're optimizing for points us to the true p of z given x, sampled from all of x, right? This is not just a specific x. And so this q of z is true right here. So, right, we're pointing down this way because we're shifting towards it. However, when we move towards it, we can see that in this case, the relevant task, because it's relevant as we shift our prediction of the internal reward, the reward difference grows a huge amount. This log q over here grows a huge amount, and this indicates that it's important, and therefore will take longer to reach this true distribution, right? Because if we're saying, oh, we got to bring it back out, then the intrinsic reward is going to go back up. And so because we're moving away from the minimum, whereas this one is not relevant, and so we're going to keep moving towards the minimum. And so hopefully that provides some understanding. You can see some empirical results here on some hard exploration problems. You can see that they, interestingly, doesn't perform super well without artificial distractions added. But that's neither here nor there. So yeah, that's just something different. Hopefully there's some valuable information. If not, that's okay too.